So let's go through this handout, okay? So in this section, we talked about inverse functions, and before we talk about inverse functions, we talk about one-to-one functions, okay? Now, you know the definition of a function, right? You have a relationship between two variables, typically x and y, right? And definition of a function is for each input, there is exactly, right, or only one output. So for each x, right, there is exactly one y. Okay? And so graphs of typical functions, right, are a straight line, right, a non-vertical line, a parabola, right, cubing function, okay? All of those meet the definition of functions, okay, the graphs, right? All three of those graphs meet the definition of function, right? They have what's called the vertical line test, right? Test whether the graph meets the definition of a function or not, right? A one-to-one function is a special kind of function. Okay. So a one-to-one function has to meet the definition of a function first, okay? And then it has this additional requirement, okay? For each output, right? So I'm going to switch the words input and output in this sentence up here. For each output, there is exactly one input. Okay. So for each y, there's exactly one x. Okay. So before a relationship can be a one-to-one function, it has to be a function. Right? It has to meet the function requirement first. And then once it meets the function requirement, it may or may not meet the one-to-one function requirement. Okay. So in example 1, so we have what is called the horizontal line test. Right? Given the graph of the function, you can determine whether it's one-to-one based on the horizontal line test. Right? And it works similar to the vertical line test. So in example 1, you determine whether the given function is one-to-one. So the first function is a transformation on the cubing function, right? We have x cubed plus 1. So this is the graph of f of x, right, is the graph of the cubing function shifted up 1 unit. Okay. So I'm going to color chalk. So instead of this cubing function, this is actually the graph of the cubing function over here. Okay. Instead of snaking through the origin, it snakes through the point y equals 1 on the y-axis. So it looks something like this. So you can see from the graph, right, it's a function, right? This graph meets the definition of function, passes the vertical line test, and it also passes the horizontal line test. No matter where I draw the horizontal line, it intersects the graph in only one location. That means for each output, there is only one input. Okay? So this is the graph of a to one function. Okay. In B, we have the quadratic function x squared minus x. Right? And the graph of a quadratic function, you know, is a parabola. So, for this particular quadratic function, okay, the minimum is in the fourth quadrant, and the parabola looks something like this, right? It goes through the origin. And you can see, right, the graph of a parabola meets the definition of a function, right? Passes the vertical line test, but it fails the horizontal line test, right? Wherever I draw the horizontal line above the minimum point, right, it intersects the graph in two locations. So there are two outputs. Excuse me, for each output, there are two inputs, okay? So for this value of y right here, we have two y's, right, two output. For this one output, we have two inputs, two values of x. For each output, there are two inputs, okay? There will only be one input. So this is a function but not a one-to-one function. Okay. Some functions are one-to-one and some are not. Okay. Okay. So why do we care? Because only one-to-one functions have inverse functions. So this function has an inverse function. This function does not have an inverse function, right? Only one-to-one functions have an inverse function. And that's what it's saying down here below. The function f has an inverse function, f inverse. This is the -1 in superscript does not mean reciprocal, right? That -1 in superscript means this is the inverse function of the function f. Okay. So function f has an inverse function, f inverse, if and only if f is a one-to-one function. Okay. So the graph of a one-to-one function and its inverse, okay, are reflections of each other about the line y equals x in the coordinate plane. So we'll do an illustration here. People ask, where did you get those functions? And I just pulled them out of the air. Okay, I just made them up. So here's coordinate plane. And here is a graph of a one-to-one function that I made up. Okay. And you can see no matter where I draw the horizontal line, it intersects the graph in only one location. And this is also the graph of a function because it passes the vertical line test. Okay. And so here is the point 0, 1. Right, there's the y-intercept. And this point up here is the point 2, 3. And this point out here is the point minus 8, 1/2. Okay. So this is the graph of y equals f of x. Okay? It's a one-to-one function, and so it has an inverse function. The graph of its inverse, now here's the line y equals x, right? It's a 45-degree line that goes through the origin. Okay? And so I drew it with dash, is a dash line. Okay? So this is the line y equals x. Okay? The graph of the inverse function for f of x, right, is reflected across that diagonal line y equals x. Okay? So the graph of the inverse function, right, is a mirror image of the graph of the one-to-one function f of x across this line right here. Okay? So how do we graph the inverse function? To graph the inverse function, all you have to do is reverse the x and y coordinates here and plot those points. Okay. So here we have the point 2, 3. So if we reverse the x and y coordinates, we have the point 3, 2. And so we plot the point 3, 2. Try to get this halfway to scale. Here's the point 2, 3. Right? Here's 3 on the y-axis, right? Roughly 2 on the x-axis. Right? So here's the point 3, 2. So if the point 2, 3 is on the one-to-one function, the point 3, 2 is on the inverse function. Okay. The point 0, 1 is on the one-to-one function, so when I reverse the x and y coordinates, I get the point 1, 0. I'm not getting this exactly to scale, but you get the idea. So here's the point 1, 0 on the x-axis. Okay. That's a point on the inverse function. This is the point on the one-to-one function. And then we have the point -8, 1/2. So when we reverse the x and y coordinates, right, here's x equals 1/2, and here is -8 down here roughly. So this is the point 1/2 -8 on the inverse function. And now when I draw a curve through those points, I get the graph of the inverse function. And you can see, right, to the best of my ability, the graph of f of x is a mirror image of the graph of f inverse of x, right, across this diagonal line, y equals x, and vice versa. So, given the graph of a one-to-one function, you can find the graph of the inverse function just by switching the x and y coordinates. Okay. Then it goes the other way. If you have the graph of the inverse function, you can find the graph of the one-to-one function just by switching its x and y coordinates. Okay. All right. Any questions on that? So we're going to be dealing with a lot of one-to-one functions going forward in this class. Where we'll be graphing their inverse, and we can use this technique given a one-to-one function, right? Graph of a one-to-one function, we can find the graph of its inverse using that technique. Okay. All right. There are certain properties of inverse functions. And so I'm not going to read through these, but we'll highlight certain ones as we go. Okay. So in example 2, we're given the function f of x is equal to 6 over x cubed plus 9, right, is a one-to-one function. Without finding its inverse, determine the value of f inverse inverse of minus 1/3. So, property we're going to use in solving this example is if f of x is a one-to-one function, and we have the case where the function f at x equals 2 is equal to 3, okay, f of 2 is equal to 3, then f inverse of 3 is equal to 2. Okay. The inverse function works in the opposite direction of the one-to-one function. Okay. What comes out of the one-to-one function goes into the inverse function, and what goes into the one-to-one function comes out of the inverse function. Okay. So if f of 2, and I just made this up, right? So f of these numbers. So f of 2, if f of 2 is equal to 3, and f is a one-to-one function, then it's also true that its inverse at x equals 3 is equal to 2. Okay. So if f of 2 is equal to 3, then f inverse of 3 has to equal 2. Okay. All right. So we're going to use property number 3 here in solving example 2. Okay? That's what property number 3 is alluding to, right? This situation right here. Okay? And so we have, for some value of x, for some value of x, f of x is equal to minus 1/3, right? And f inverse of minus 1/3 then has to be equal to whatever that value of x is. Okay? We're just doing what we did over here. Only now, right, we know this y value that comes out of f of x, which goes into the inverse function. Okay? What we don't know is the value of x in f of x that produces minus 1/3. And we can figure that out without actually calculating the inverse function. Okay? And plugging in minus 1/3 into the inverse function. Whenever I draw a graph like this, when I erase it, I feel like I'm destroying a record. I mean, it's like my finest work. Okay. Drawing good pictures, right, is a talent. Okay. And I always struggle with that one. All right. So we have f of x, right? We're given the one-to-one function f of x is equal to 6 over x cubed plus 9. Okay. But we know, right, that for some value of x, this is equal to minus 1/3, right? So we can set the right-hand side equal to minus 1/3, and then solve for x. So that will give us the value of x, where f of x is equal to minus 1/3. Okay. Well, this minus 1/3 on the right-hand side can be written as 1 over minus 3, right? Minus 1/3 is the same as minus 1 divided by 3, which is the same as 1 divided by negative 3, right? Use your calculator, you get the same decimal value, right? All of them are equal to negative 0.333 repeating, right? 3 repeating forever. cross multiplication from high school. You got a fraction on the left equals fraction on the right. So I can do the cross multiplication. And so when I do that, I have x cubed plus 9 times 1. Let's just write it out. And that has to equal 6 times minus 3, or minus 3 times 6. Okay. So all I did was the old trick from high school. Cross multiplication. Okay. So x cubed plus 9 times 1 is x cubed plus 9, and on the right hand side, minus 3 times 6 is negative 18. We're solving for x, right? So we subtract 9 from both sides. We have x cubed is equal to minus 27. And now we take the cube root of both sides. What's the cube root of minus 27? Negative 3, very good. So x is equal to negative 3. So without finding, right, this is the question, without finding f inverse, determine the value of f inverse of minus 1/3. So we have f of minus 3 is equal to negative 1/3. So f inverse of minus 1/3 has to be equal to negative 3. Okay. What goes into the one-to-one function comes out of the inverse. What comes out of the one-to-one function goes into the inverse. Okay. The order is just reversed. Okay. Any questions on that, ladies and gentlemen? Okay. In example 3, it says, given f of x is equal to 1 over x minus 4, and g of x is equal to 1 over x plus 4, verify that the functions f and g are inverses. So we're going to use property number 5, okay, to verify that f inverse is the inverse of f. Show that this is the composite, right? This is f inverse of f of x equals x, and the composite f of f inverse of x is equal to x. Okay. So this is the composite of f inverse with f, and this is the composite of f with f inverse. Okay? So we're going to do two composites down here in example 3. We're going to do the composite of f with g and the composite with g with f. And if the result of each of those composites is equal to x, then we know f of x and g of x are inverse functions of each other. Okay. So, almost wrote on the board on mark. Highlighter. So you have f of x is equal to 1 over x minus 4, and g of x is equal to 1 over x plus 4, So we're going to do the composite of f with g first, right? Which is this fancy notation, right? Composite f with g is a function of x, which is equal to f of g of x. What's the first step? Replace g of x with what it's equal to, right? So g of x is equal to this. So we put that in for g of x. So we have f of 1 over x plus 4. And now to evaluate f of 1 over x plus 4, right? We put 1 over x plus 4 in for x on the right hand side of f of x, right? We have 1 over x plus 4 minus 4. This is a complex fraction, right? You gotta simplify. Here's the main denominator. 4 minus 4 is 0. So we end up with 1 over x. And we've had this conversation already this semester. When you divide 1 by a fraction, what do you do to the fraction? Just flip it over, right? Dividing 1 by fraction, you're just taking the reciprocal of the fraction. So this is equal to x over 1, which is equal to x. So the composite of f with g is equal to x. So we're half done in showing that f of x and g of x are inverse functions of each other. Now you got to take the composite of g with f. Okay. And the composite of g with f is equal to g of f of x. Okay. And first step is to replace the inner function f of x with what it's equal to. Well, it's equal to 1 over x minus 4. So this is equal to g of 1 over x minus 4. And now to evaluate g of 1 over x minus 4, we put 1 over x minus 4 in for x on the right hand side of g of x. And we have one over x minus 4, right? So we have a complex fraction. This is the main numerator. This is the main denominator, right? 1 over x minus 4 plus 4. Again, we're dividing the number 1 by fraction. So that means just take the reciprocal of the fraction, right? This is just equal to the reciprocal of the fraction. So this is equal to the reciprocal of 1 over x minus 4, which is x minus 4 over 1. And x minus 4 over 1 is x minus 4. Anything divided by 1 is itself. And minus 4 plus 4 is 0. So this is just equal to x. And so f of x, the composite of f with g is equal to x. And the composite of g with f is equal to x. Okay? So f and g are indeed inverses of each other. Any questions on that?